We're starting a series of problems right now with a small amount of ice that we're going to heat up and watch it as it changes phases from ice to liquid water to water in the gas phase. But in this first step, our focus is actually not going to be on the ice at all. It's going to be on the energy that makes its way into the ice from another source. In the lab, we often use a Bunsen burner like this one down here to heat things, and we can do that with most anything. And in this particular problem, we're going to heat some ice. But like I said, the ice itself isn't important. What we want to do is find out how much energy can we get from that flame, from that Bunsen burner. And what we have to remember is that in the lab, when you use a Bunsen burner, you're essentially combusting a gas, and that gas is methane gas. It's CH4. And you know that when you uh, have a combustion reaction, that gas combines with oxygen to produce CO2 and H2O. We should probably go back and balance this equation. So I've got one C on each side. I'm going to put two in front of H2O to give me four H's. That gives me a total of four oxygen, so I need a two right here. This is a balanced chemical equation. It's not necessarily what the title of this slide suggests, a thermochemical equation. Thermochemical equation is going to have one more piece of information. It's going to tell us something about how much heat is produced in this reaction. So I happen to know this. This is a published piece of data. You could look it up, or it would oftentimes be given to you. But there's something called the heat of combustion, and it's published for pretty much any compound that burns like methane does. And I know that methane is negative 890.4 kilojoules per mole. Now, this mole part could be confusing. We could think of it as per mole of equation. In this case, we're going to say it's per mole of CH4 that is burned. Now, in the equation, if I want to turn it into a thermochemical equation, I'm going to add 890.4 kilojoules to the right side of this equation. That makes it a thermochemical equation. What's somewhat confusing for students is, why is it that here in the data I have a negative sign, but here in the thermochemical equation I have a positive sign? Well, when it's published as a standalone number, we need to indicate somehow that energy is being released. And for us, that negative sign tells us that energy is being given away. It's being given off by the combustion of this methane. But we leave it as positive in the thermochemical equation because it shows up on the product side. In other words, we know that it is energy given away because it's being produced. It's on that product side of this equation. So in the particular problem that we have here, it says 0.0742 grams of methane were burned to heat up some ice. How much energy was produced by burning the gas? So I know how much gas I have, 0.0742, and that's grams of CH4. And I want to find out how much energy. Energy could be given to us in joules or kilojoules, and we have right now before us a piece of data that is going to get us there. Here's an important thing. The bottom half of that unit is moles. So I know the very first thing I want to do is change those grams into moles. And so I'm going to go to the periodic table. I'm going to add together the molar masses of 1 carbon and 4 hydrogens, and I get 16.01 grams of CH4 for every 1 mole of CH4. And then all I have to do to finish out is say in 1 mole, I produce minus 890.4 kilojoules. I go to my calculator, I say 0.0742 times negative 890.4 divided by 16.01, and I get 4.13 kilojoules. And it actually should be negative 4.13 kilojoules. That's the energy produced in this reaction. Now, we'll often need that value to be in joules. So know that if we want to go from kilojoules to joules, I'm going to have to multiply that by 1,000. And so when I do that, I get minus 4,130 joules. In our next problem, which we're going to do live in class, we're going to take that answer and we're going to figure out what does it actually, um, what happens to that energy when we put it into some ice. So we'll see you in a couple of minutes and we'll take a look at where that energy goes. See you then.